So the overall goal of this project was to introduce program synthesis features into Pyret in a meaningful way for the context of novice programming. So basically, to give a brief introduction on Pyret, here's a Pyret program on the left side of the screen. It's Python-like syntax, but the programming language itself is based in JavaScript, and so it can run in the browser. It compiles to JavaScript and can run in the browser. The Pyret team has built this pretty sophisticated IDE that also runs in the browser, and from this IDE you can run Pyret source code and also type check and run Pyret source code. So the type checker was of particular significance for this project, and I'll talk about why in just a minute. So the original idea for my project was to introduce program synthesis features into Pyret for an education context. So there's some unique challenges with this because program synthesis is about constructing valid programs from particular specifications. And so that means the result of synthesis is actually a complete program that works on the inputs that you wanted it to work on. So this is a problem in the education context because we don't want to actually produce finished programs for students. Instead, we want to encourage them to use good programming practices, and instead we want to reward them for using those good practices by helping them out in meaningful ways that they can still learn from. So the original idea was kind of to encourage good use of testing suites for functions, so basically writing thorough unit tests for functions, and also to encourage sophisticated type annotations for functions. The reason we wanna encourage the use of these two is because both of these are really critical tools for guiding the search in program synthesis. This is kind of the bottleneck in program synthesis. So we need ways to kind of prune the search space so that we're not taking forever to actually create a program that works. So the original idea was to utilize this native feature of Pyret. If you can see here, this ... expression. So Pyret supports this, and it's called a template expression. It basically means this expression is unfinished. I don't know what to put here. And so what we want to do is allow students to kind of explicitly put these in their code as places where they may want help. So we won't immediately offer them help. So instead we want to kind of find evidence that a student has been struggling and start to make meaningful suggestions at that point. So the original idea was to, instead of presenting them with complete programs, we wanted to present students with multiple candidate programs, some of which may even be incorrect, but still allow the user to choose a program by making judgments about the validity of the program, how efficient it would be, the complexity of the implementation, so on and so forth. So in this way, we're not giving students a cop-out, but we're instead encouraging them to make good judgments about code and read foreign code that they didn't write and make judgments about those as well. The other thing that we want to encourage in this project is good programming practices, like I mentioned earlier. But in particular, the original idea was to utilize testing suites. You can see an example of a function testing suite right here in this where block. So this where block is associated with this isBST function. So we want to encourage writing really good test suites because it can actually help us produce better synthesis results, and I'll talk about that in a minute. So in the interest of actually completing something on time for the quarter, I had to revise this idea a little bit, especially because I was working in kind of an unfamiliar environment that I had never written code in, which was the Pyret type checker. And so the revised idea was to basically use this ... as a marker for the user indicating they want completion results, code completion results. So the way I do that is actually, if I see a ... in the source code, I can suggest to the user names, as in bound names, that match the type that this expression should have as replacements for this expression. So for this particular case, we can see that the type for this expression would be BST. We can see this because the function is annotated as having return type BST. So any expression within the function body should evaluate to type BST. So because we have a cases expression here, each branch of the cases expression should also have type BST. So because of that, we can propagate the type BST all the way forward to this ... expression. So based on that, I can search through the context of the entire program so far up to this point and present alternatives to the user. And we'll see an example of that right now when I actually run the program. So once I actually run the program, you can see that my modified type checker is giving suggestions like leaf right here, this node constructor right here, and t. So what are each of these? So leaf is actually this constructor here, which is a constructor for the type bt. So we can see that type BST is actually a refinement on type BT. All that means is type BST has the same constructors as type BT, but has an additional requirement that values of this type validate against this function. And all this function does is check that a given binary tree is actually a BST. So based on that, we can see that both of these constructors for the type BT would be valid replacements for the template expression right here. So that's why I present both of those. Another replacement that's valid is the in-scope variable t. So t is actually one of the parameters to the function, but I've explicitly annotated it with type BST, so it's a valid replacement for this ... since it's in scope and has the type that I should have for the template expression. You may notice that I suggest a call to the node constructor, but I don't actually specify any arguments. So this was another compromise I had to make to actually complete the task on time. Future work could actually recurse on each of the arguments for these constructors and provide the user with instances of the types that actually go in those constructors' arguments. So the implementation for this was pretty tricky. As I said, I was working in an existing programming language with like a really sophisticated type checker. So I actually couldn't use a lot of the type checking results built into Pyret, so I just had to manually walk the AST of the entire program and look for instances of these template expressions. So while I was walking the AST, I would have to manually forward propagate the type that I wanted. So for example, once I encounter this function declaration, I can find out the return type of the function, and I know that that must be the type of any expression within the function. And again, for this cases expression, because the type for the surrounding expression was BST, I can propagate that to each of the branches in the cases expression. And so that's how I know once I'm at this point that the type I expect is BST. So once I have that information, I just search linearly through the context of the entire program for any names, any bound names that match the type BST. And those match the three that we saw on the right side. So I want to talk briefly about the value this would have in CS education. So like I said, we don't want to just provide students solutions to assignments. Instead, we want to encourage positive programming practices by offering students, by kind of pushing students in the right direction based on those good practices. So what that means is, like I said, we want to encourage students to write thorough test suites because thorough testing suites would allow me to very easily find out more expressions that I could possibly replace with this ... So for instance, I could add a quick test case to this and say if I want to insert into the BST that looks like this, the value 1, then I know that this should look like this. It should insert the 1 to the left of the root, which is 2, and this is how the resulting BST should look. So I can actually symbolically execute the function on this input because the user explicitly provided it. So because I have this BST, this would be the t in the function, and I can actually match this input to the cases in my cases statement. So I know that this would match this branch because it's a node constructor, and because I can match it on this branch, I know that the output for this input case should look like this. So I can just instantiate the cases branch with this output, and this would be a valid expression, meaning it would type check, but it may not be the correct solution for actually inserting. Basically, I would do this iteratively for all of the tests that the user provides, because presumably they'd be providing more. Clearly, the more tests the user provides, the more I can refine this result and actually present more meaningful suggestions. So again, this is a stretch goal and something that I want to work on in the future. I've already kind of begun this project and I want to continue working on it over the next few quarters. And I think this has some really powerful applications in CS education. I think there's definitely some legitimate research to be done as to the effectiveness of program synthesis as an education tool. But I think that looks promising, and I'm excited to see where it goes and even keep you updated throughout the next couple quarters.